Okay, welcome back. Yesterday, what did we do? We did surface area. Okay, and what we did, we specifically had chosen those surfaces as those which can be parametrically represented. Basically, what we did, we were dealing with some surface in 3D, surface in 3D, I'm calling it S. So then, if I take a point on that surface, suppose I join that point with the origin, So then, this vector, let me call it R, it can be described in terms of a transformation, from some domain in R2 plane. We are going to call it UV plane, okay? Say corresponding to some point here, we will get a point lying on this surface, and the coordinates x, y, and z, they are going to be some functions of these two variables u and v. Okay, so similarly y and likewise for j, we are going to get it. Okay, so now if you further recall, and when we define the surface integral, what we did, we considered a rectangular domain here. And then what we did, we divided this rectangular domain into some sub-rectangles, and corresponding to this, I was getting on this surface again. These lines, it corresponded to some curves like this, okay? And what we had, we corresponding to a particular subrectangle here, we found a curved rectangle on the surface, right? And from there, we derived the formula for surface area. Okay. Now, one thing I would like to mention is that, see, if you recall, suppose this is my domain D. So then, what happened? This area of this surface, it was given to me as simply RU plus RB your dA, right? I have this formula. Now, one thing you have to remember that here D was considered as a rectangular domain, but it is not necessarily so that it is always going to be a rectangular domain. It can be any general region there in R2. Okay, so this dA and D, they are related by, you shouldn't take D to be a rectangular domain all the time. It is going to depend upon how the surface has been defined, or how you can define this surface in terms of RUV, Okay, so I will do 2-3 more examples, then it will be clear to you. Okay, fine. So now, yesterday we have already derived from this formula what is going to be the area of the surface of revolution. Okay. Before, in fact, although I had taken the long route, that could have been accomplished much easier. Okay. How it is so? Let me, as I have told you, that sometimes a surface can be the graph of a function of two variables, right? So in that case, if the surface is given to me by z equal to f of xy, then what I am going to do, I am simply going to use this parameterization where it is going to be simply given by your xi plus yj plus f of xyk, right? Now, if you look at this formula, so then what I have to find out, I have to find out Rx, right? And Rx is simply going to be I plus your fxk and your Ry, this is going to be equal to j plus fy. Okay, so then your Rx cross Ry, this is going to be ijk 10 fx 01 fy, and this is going to give you what? Minus fx I minus fyj plus. Is it okay? Fine. So now, so I'll come back to this again. This is a very interesting stuff here. So that your mod of Rx Ry, I'm having plus. So this is simply going to be what? This is simply going to be eventually your 1 plus fx squared plus fy squared, right? So that is why whenever you consider the surface to be the graph of a function of two variables, so then this formula is simply going to reduce to your d, then 1 plus maybe, I mean fx, you can write it zx plus zy squared dA. That's it. Okay. So now for surface of revolution, if you consider your this your rxy to be equal to xi plus what's it xi? Yeah, fx is r x theta cos theta j plus fx sin theta k. So can we do it from here? No, we cannot do it from here. Anyway, fine. Sorry. I mean, you stick to whatever I have done yesterday. Okay. So now another thing I want to mention here. Suppose I consider this surface J. And this can be written as a level surface. Like something like f of xyj. This is equal to j minus small f of xy, and this is equal to some constant. In that here in this particular case, that constant is equal to g. Is it okay? Fine. So then you know that grade f is a normal. To the surface f of xyj equal to constant. Is it okay? Fine. Yeah. Fine. So in this particular case, then grade f is going to be given by what? It is simply going to be given by your what? Your fx, fy, fz. So this is simply going to be minus fx minus fy 1. Right? And we have already told, how this concept came about. We have already told that your we consider the tangent plane, isn't it? We consider the tangent plane at a point, and then at that point, the normal it came out to be this, isn't it? This is exactly what is happening here. Is it okay? Right? So whatever approach you take, it is going to, arrive at the same conclusion. Okay. Now, if you want to find out, the unit normal, to a parametric surface, so then that unit normal, if it is n cap, it is simply going to be given by this divided by its magnitude. That's it. Okay. So let's try to work out one example. So this part I have already. Okay. So this exercise we have already done, but let us try to do it through this approach. So you have to find out the area of the part of the paraboloid z equal to x squared plus y squared, z equal to x squared plus y squared, that lies your under the plane z equal to 9. Under the plane z equal to 9. Okay. So find the area of that part of the paraboloid given by D, this z equal to x squared plus y squared, which lies under the plane z equal to 9. Okay. So here it is going to be something like this, and this is 9. Okay, so here z equal to x squared plus y squared. Okay, so here this is my surface. This is my surface. This is my surface, and maybe let me just draw it completely. Okay, fine. So now you can see that the surface has been given. Surface has been given as a function of x and y. The surface is nothing but the graph of a function, right? So the parameterization is simply r xy. R xy is simply so x squared plus y squared. Okay, right? So then, if I have to find out the surface area, what I'm going to do? So area of that surface, it is simply going to be d, and then this one your 1 plus your zx squared plus zy squared dA, right? So now here d, and then this is going to be what? Zx is 2x, zy is 2y, right? So eventually it is going to be plus 4 x squared plus y squared dA. Fine. Now let us do some kind of backtracking. See here, the parameters are x and y. Now you have to see for this surface, what is the range of that parameter? So the range of the parameter is such that your x squared plus y squared is less than equal to 9, isn't it? Is it okay?
Yeah.
Fine? So here it is clear that it is x squared plus y squared is less than equal to 9. So that is why here your d is going to be your xy belonging to R2 such that x squared plus y squared is less than equal to 9. Is it okay? So that is why here, and you know that, and once you have arrived at this, so this simply becomes a double integral, isn't it? This simply becomes a double integral, and you can simply use your r theta concept. You can simply use r theta concept, right? So if you consider r theta plan, so then what is going to happen? Your r is going to go from 0 to 3, right? And theta is going to go from 0 to 2 pi, right? And this integrand is going to be 1 plus 4r square, and dA is going to be r dr d theta. R dr d theta. Is it okay? Fine? So you know how to integrate it. I don't want to do this. Okay. So now what I am going to do next, I'm going to now start your surface integrals. Surface integrals. Okay. Surface integrals. See, basically, the surface integral, you have already done multiple integral. Okay. So in multiple integral, what we did, we, like say, when we consider a function of two variables, or okay, so we had some domain, here in say xy plane. Say suppose this is D, right? And firstly, what we considered, we considered a rectangular domain initially, which later on this concept we extended it to any general region. So basically, what we did, we considered a domain into planar region. So this D is a planar region, and then we subdivided this by some rectangular grid, and then what we did, assuming that the graph of the function it lies above x-axis at the beginning. So then what we did, corresponding to each subrectangle here, we had some columns like this, right? And if I consider a point here, like say xi star, yj star. So what we did, we had simply taken xi star, y j star, and then if the dimension of this small subrectangle is delta xi and delta yj, and in many books they take it as equal, like delta x and delta y. So then what we did, we simply took the summation. I going from 1 to n, j going from 1 to n, and then we had taken the limit of this summation as m and n tends to infinity, right? So here the concept is going to be the same. The only difference is that whenever we consider surface integral, the only difference is that what we do here, if you have to evaluate the surface integral of a function, of two variables, then what you have to do, like firstly, okay. Say, suppose this is my surface. It is say S. So now, what I will assume that this surface corresponds to some region D in UV space. Sorry, time, and then you can find some mapping from here. So that each point on the surface of S, it is obtained by taking this XUVI. So basically, I should be able to express S as a parametric surface. That's it. Now, the difference between this approach, which was double integral, and this surface integral would be what you are going to do. So, see, corresponding to these subrectangles, you are going to have some curved, like these subrectangles are not planar here on the surface of S. But what we are going to do, we are simply going to consider the area of these subrectangles, right? And then what I'm going to do, that function, which is eventually we can convert it into a function of u and v, I am simply going to multiply it by area of these subrectangles. That's it. Other than that, everything is going to remain the same. Everything is going to remain the same. Is it okay? Fine. And then what is going to happen? This ds, you know that how to find out the area of that we have already found out. So this ds is simply going to be your RU cross RV, your dA. Isn't it? Is it okay?
Yeah.
Fine. So once I show you this right, it will be more clear to you. So this is how it goes. So as I have told you, like suppose that a surface S has a vector equation this, okay, where UV belongs to some domain D. And here again, let me emphasize that although this domain, it looks like a rectangular, domain, it doesn't necessarily have to be so. It can be of any arbitrary shape. Okay. We first assume that the parameter domain D is a rectangle, and we divide it into subrectangles Rij with dimensions delta u and delta v, like this. Okay. So then the surface S is divided into corresponding patches like Sij here. Corresponding patches Sij. As here. And then what we do, we evaluate F at a point Pij. Here we take a point Pij at each patch and multiply by the area delta Sij of that patch. And then you form the Riemann sum. You form this Riemann sum. Okay. And then when we take, as I have told you, the limit as the number of patches increases and define the integral surface F over the surface S simply as this. That's it. It is as easy as that. Okay. And again, you already know that the area of this patch Sij, it can be approximated as this. This we have already done earlier, right? This we have already done earlier. So that is why, and again see here, the function f, it can be a function of all these three variables, which constitutes that particular point lying on the surface. Is it okay? Fine. So this f of xyj. Although if you recall, in case of double integral, we were considering a function of two variables only. Is it okay? Can you appreciate the difference between double integral and surface integral more now? Because see what is happening here. This is a function of three variables. But again, you remember this ds, the elementary area that we are considering, it is going to be over a three-dimensional surface. Okay, fine. Whereas earlier, whenever we consider the columns, they were lying above some planar region. Okay, so that is the difference. So this is what it is. This is what it is. So this is the formula. This is the formula. So everything remains the same. Only thing is that you have to rope in that function. So again, you know that if that surface is a graph of a function of two variables, you know how to convert this RU cross RV there, right? So we can work out some examples. So this you can easily work out. This I have already done. Like say that sphere thing I have already worked with. What is going to happen to RE cross RV? You already know that you are going to get something like what this is going to be a square sine phi if you use theta phi transformation. Okay. Now I like to do more here, but let me say a surface integral of the graph of a function. It is pretty straightforward. See, if the surface is given by z equal to g of xy, z equal to g of xy. So then this converts into this one, because you know that expression under the radical sign, that is simply your mod of Rx cross Ry. Is it okay? Fine. So this is the way. This is the way we are going to do. So, and let us do one example, and then I will do it for, when a surface is the union of multiple surfaces. Okay. So here, evaluate. So you have to evaluate. You have to evaluate ds, where s is the surface, x plus y squared. Okay. So here you can see that this is nothing but z is given in terms of the graph of a function of two variables, right? Graph of a function of two variables, and again you can see the range of x and y, right? The way it has been given, it is nothing but a rectangle. Okay, so our job is going to be much straightforward. So this y ds, so this is simply going to be, now this I'm going to convert it into d, then y, so 1 plus zx squared zy squared, then your dA. So this is going to be what? X plus y squared. So y 1 plus 1 plus 4y squared, right? dA. And this is, let me still keep it like this, 2 plus 4y squared dA. So now we can integrate it. So what I'm going to write it as your, because okay, let me 0 to 1, y equal to 0 to 2, then 8y 2 plus 4y squared dx dy, or dy dx, whatever. I mean, it doesn't make any difference, because you know that here the function is it is of variable separable type, right? So this is simply going to be 1 by 8 into 1 for the x part, and for the y part it is going to be what? 2 by 3, 2 plus 4y squared to the power 3 by 2, 0, 2. So you just work it out. This is straightforward. So now I would like to come to another of these concepts. This is pretty straightforward, whatever is going to be shown. So the answer is given, you can work it out. And this is some application of this surface integral. So if a tin sheet, like say aluminum foil, has a shape of a surface S and density, that is mass per unit area. So this is going to come into picture again, hopefully today itself. At the point xyz is rho xyj. So then the total mass is simply what you have to do. You have to integrate the density function over that surface. That's, and the center of mass is given by this with this other formula. Okay. So now I'd like to reach this one. Surface integral for piecewise smooth surfaces. Okay. So now if you have, like say, a surface, it is not necessarily smooth all around. It may be, the union of some piecewise smooth surfaces. Say, suppose it is the union of some piecewise smooth surfaces S1, S2 up to Sn, and that intersect only along their boundaries. Okay, so then the surface integral f over S is simply defined as this. This is pretty obvious. So let us work out a particular example. So this example, it is going to illustrate a lot of stuff. Some concepts, I think it will be more clear once you work it out. Now, see what it is. You have to evaluate. Surface integral of Z over the surface S, where here see this S is nothing but combination of three piecewise smooth surfaces. This is S1. So S1 is this one. It is given by the cylinder x squared plus y squared equal to 1. Your S2 is nothing but this disk at the bottom. It is simply x squared plus y squared equal to 1. This is the disk, x squared plus y squared equal to 1, z equal to 0. But for this S1, it is x squared plus y squared equal to 1, z equal to j. Okay. And then thirdly, you have this plan. You have this plan given by j equal to 1 plus x. Okay. So you have to evaluate this integral. So how to go about it? Okay. Fine. So I have it like something like this. Okay. So then here I have. Okay, so it is basically combination of three surfaces. One is this x squared plus y squared equal to 1. Of course, this one is x squared plus y squared equal to, it is less than 1 if you consider this surface, right? J equal to 0. Okay, and this one is the plan. This plan, it is given by j equal to 1 plus x. Okay, and we have to evaluate this jts. Okay, so let me call this one as S1. That this can be base, and let me call this plan given by j equal to 1 plus x. This as say S2, and this one like that cylindrical surface, this as say S3, because I would like to evaluate them in that order. Okay, so I'm keeping the most difficult part for the later. Okay, fine. So now you know that this is simply going to be this S1 JDS plus S2 ZDS plus S3 ZDS. Okay, so now you can see that over S1, what happens? Your Z is equal to 0, isn't it? Right? Over this, right? So that is why this integral is going to give you 0. Fine. Now let me come to S2. So S2, again, this surface, your z equal to 1 plus x. You forget about this integral. That will come later on. We will be able to deal with any integral which is a function of x, y, z. So firstly, you look at what is j over that surface. So z equal to 1 plus x. Okay. So what I can do, I can write r to be equal to your xi plus yj plus 1 plus x k, isn't it? Find any point xyz line on that plan can be represented by this vector, isn't it?
Yeah.
Right? So that means I'll dissect it once again. So that means your if I let me do it here itself, rx cross ry, rx cross ry here, it is going to be I j k. So then it is going to be simply 1 0 1, right? 1 0 1, yeah, and then 0 1 0. Am I correct or not?
Correct.
Yes. So then this is going to give you what? This is going to give you minus I. J is 0, right? And k is 1. Yeah. Plus k. Minus I plus k. Okay. So that your so this is going to imply ry. This is simply going to be equal to square root, right? So if I want to evaluate, so this S2 then the ds, okay. So then this is simply going to be your d square root 2z dA. Okay, so now let us come to the point. Now, what is d here? What is d here? What is d here? And of course, I'll change this. So j is your 1 plus x, right? And what is d here? If you consider here, if you consider this particular surface, So for this particular surface, all the xy they lie in this disk, isn't it? Right?
Yeah.
Right? So basically, again your like say if I call it say D2, if I call it D2, so then D2 is simply xy belonging to R2 such that x squared plus y squared is less than equal to 1. X squared plus y squared is less than equal to 1. So that is why what I can do, I am going to make use of now. What? That polar coordinates. So that is going to give me your again r goes from 0 to 1, theta goes from 0 to 2 pi, and this, and then square root 2 1 plus r cos theta r dr d theta, r dr d theta, and you know how to integrate it. So basically, what is going to happen, right? This is going to give me. This is going to give me your 2 0 to. Should I do it with respect to r first and then we do it with respect to theta? It will be easier. Don't worry. Not to be worried about it. So it is going to be your r into theta plus r sine theta, theta equal to 0 to 2 pi dr, right? Okay, yeah, fine. Yes. So obviously, this is going to give me, because sine 0 and sine 2 pi both are 0. So it is going to give me 2 root 2 pi. Then you're simply r square by 2, right? R going from 0 to 1. So eventually it is half. So root 2 pi, right? It is going to give me root 2 pi. Okay. So fine. So now let me come to the third part, which is the most interesting one. Okay, so now let me come to the surface of the cylinder. Surface of the cylinder, x squared plus y squared equal to 1. So now here on this surface of the cylinder, you can see it is something like it is something like it is something like, say, if I show you only a half part, it is going to be something like this. It is going to be something like this, isn't it? It is going to be something like this. This you have to, I mean, expand it further, right? So now, if you look at S3, if you look at S3, you take any point x, y, z belongs to that. So, like say R, so this is equal to your xi plus yj plus zk, yz plus zk. So then, I mean, what we are going to do? Because again, you can see that your xy, they lie, I mean, in this disk, isn't it? Are you getting the point? In this disk. But now I have a problem that this cylinder is x squared plus y squared equal to 1 and z equal to z, right? But here you can see that for all the points xy lying in this disk, what I can do, I can simply use cos theta I plus your what? Sin theta j. Is it okay? Fine?
Yes.
Yes, sir.
So I can simply keep j as j. So basically, this has become your theta j. I simply need two parameters. Is it okay? Fine?
Fine, sir.
Yeah.
So now, here what was happening? Like say, while I mean trying to find out earlier what we did. In both the cases, your S1 and S2, what we were doing, we were considering this UV, to be simply your UV plane, simply to be your XY plane. Okay, simply to be XY plane. Because the, I mean, X and Y, they varied from, I mean, they simply lie on that, on that disk. Although later on we simply converted them into some polar coordinates, but basically we were considering x1. But now here you can see that in this particular case we are considering your theta j. Okay, and what is the extent of j? Here the j goes from j equal to 0 to j equal to 1 plus x, isn't it? So that means your j lies between 0 and 1 plus cos theta. Is it okay?
Yeah.
Fine.
Yes,
So I'm going to change it again. Just Okay, so now what I'm going to do, okay, so this is theta, this is 0, this is 1, this is 2. So this is 0, 2 pi. Just pi by 2. Okay, so what is happening now? Your D is this, basically D3. D3, this is the shaded portion. Shaded portion is the region, which is going to be all points. I mean, theta z here, they are going to be mapped onto those points lying on that surface. Are you getting my point? So my situation is going to be like this now. Okay, so that means, so if I have to perform this integration S3 Z ds, so this is simply going to be, this is a D, maybe I can call it D3. So Z is your 1 plus cos theta now, isn't it? Right? 1
Yeah.
plus cos theta, right? And ds, ds is simply what? Now, again, what you have to do, you have to find out your r theta cross rj. So this is what? I, j, k, r theta rj. So this is going to be minus sin theta cos theta 0 and then 0 0 k. Am I okay or not?
001.
001, sorry. Okay, 001. So 001. So for I, it is going to be cos theta I plus, I think it will be sin theta j, right? Sin theta j and k is 0. Yes, right? So that means for this, your r theta rj, this is simply 1, right? Mod of that.
Yeah.
This is simply 1. So that is why that is what I can do. I can write it as okay. Let me write it r theta rz dA. So eventually, what I can do, I can write it as theta equal to 0 to 2 pi. Then j goes from 0 to 1 plus cos theta, then 1 plus this cos theta, and then this is simply 1, then dz d theta, dz d theta. Okay, so then from here, what you can get 0 to 2 pi, and then this is simply going to be what? 1 plus cos theta square. Isn't it?
Yeah.
Right? So
Yes.
1 plus cos theta, yeah, 1 plus cos theta square. Is it or
Into
not?
2 pi.
No, just a minute. J is there, na? 1 plus, just a minute. And anyway, this is independent of J. So eventually, it is going to be 1 plus cos theta squared d theta, right? Am I correct?
Yes, this is
Sorry. Just wait a minute. Sorry. No, this I should not do. this Z is Z now. So simply Z this. I don't have to convert Z into that because this is Z TZ, right? Z goes from, isn't it? I'm not going to convert
Okay.
because this is limit for Z only, isn't it? This is the mistake I have done. So this is simply going to be 1 plus cos theta. Yeah, just tell me. Z is Z square by 2, right? Yeah, 1 plus cos square by 2. I think. Eventually, I would have got the same thing. Z is Z. Did I miss something here? I think I should be okay. Yeah, it should be something like this. Yeah, I'm fine. I'm fine. Okay, so then this is not going to be that hard, I'm telling you. So 0 to 2 pi. This what you can do. This is simply 1 plus 2 cos theta. Then again your cos square theta, right? So cos square theta you can write as half 1 plus cos 2 theta. And you can easily integrate this. Okay. So if you integrate this, it will come out to be 3 by 2 pi. Because I have the answer in this slide, that is why. Okay. So this you can easily integrate. So now I think it is clear. I mean the reason what you should get. See, I think I would have ended up with the same expression, even if I had taken 1 plus cos theta here. It won't have mattered. Okay. It won't have mattered, but I mean because the limits of this is 1 plus cos theta, like again it is like, right? So yes. So this is about your area of the surface integral. So next thing what I'm going to do now, I'm going to talk about oriented surface. I'm going to talk about oriented surface. Okay. See, whenever we consider a surface, whenever say suppose this is a surface. Okay. So then this surface is such that you consider any point. I can consider a normal here. This is your outward normal, and similarly I could have at the same point I could have taken an inward normal, isn't it? And that was possible because this has two sides. This has two distinct sides. Okay, so such surfaces, they are called oriented surfaces. So you may be thinking that why cannot all surfaces be oriented surface? So for that, let me give you one example. See here I have considered this strip. Okay, I have considered this strip. The one is, I mean, one side is of kind of, I mean, green and white color. The other side is completely white. So now, if I roll it like this, fine. So then what is going to happen? If I consider this as a surface, so then it has two distinct sides, isn't it? This side and this side. Okay. So now, if you are at this point, say, if you are at this point, and you want to, I mean, come back to the back of this point, exactly on the other side of the surface. If you want to come there, what you have to do? You have to cross these edges, isn't it? You have to cross these edges here. Are you getting my point? This edge, or edge towards left, you will come from here. Then, say, suppose some ant is, I mean, moving from this point to exactly the point on the other side, which is at the back of this point. So then you have to cross these edges, this edge, right? Now, instead of that, if I construct a surface like this by joining it, if I construct a surface like this by joining them to be something like this, say, suppose, let me staple it here. So now I have a surface like this. So now you think about an ant moving along this surface from this point. So he will move along this point, and then he will go, and he will reach exactly the point which is the point on the back side of this surface, right? Without crossing it, without actually crossing the surface at its edge. Are you getting my point? Right? So this is nothing but a Mobius strip. This is nothing but a Mobius strip. And this one, the Mobius strip, I mean the surface which comes out of this Mobius strip, it is not an oriented surface. Okay? So that is the meaning of oriented surface. So where you must have two distinct sides. So basically, you must be able to draw at each point of the surface two normals, one outward and the other inward. Okay? So let me quickly. So this is about, and see if we that those two normals, suppose we consider a unit normal, unit outward normal. If I denote it by n1, then the inward normal n2 is nothing but minus n1. Okay? See, if it is possible to choose a unit normal vector n at every point, every such point x, y, z, so that n varies continuously over S, then S is called an oriented surface, and giving the choice of n provides S with an orientation. So basically, if you can think about all the normals lying on that particular surface, you have an idea about the orientation of that surface. Okay? So this is a non-oriented surface, as I have already told you. So now I am going to go to this you already know. I mean, if the surface is given as the graph of the function of two variables, so then this I have already worked out. So then you know that a unit normal vector is given by this, because the expression in the numerator, this is simply nothing but Rx cross Ry, isn't it? This we have already worked out. Okay, and if S is a smooth orientable surface given in parametric form by a vector function R u v, so then it is automatically supplied with the orientation of the unit normal vector. This is obvious, right? How to find out the unit normal vector on a surface, you can easily work out. Okay, and here in this particular example, because already you know Ru plus Rv, that came out to be your like Ru plus Rv, that this, if you work this out, you will find out that this is nothing but a vector in the direction of the radius, and that is obvious because if you join any point of the surface of the sphere, right, and if you consider that vector joining any point of the surface of the sphere to the origin, so then you know that that is going to constitute a normal to the sphere. Okay, so that is why. So this interesting example is that. Okay, so now what I'm going to do for a closed surface, that is a surface that is the boundary of a solid prism E, the convention is that the positive orientation is one for which the normal vectors point outward from E, and inward pointing normals give the negative orientation. Okay, so I don't know whether you have understood that or not, because we have been talking about orientation. So what it is, I don't have any glow or something like that. See what it is saying. Say, suppose I consider a sphere. Okay. So all vectors on the surface of the sphere that is coming outside of the sphere. So I am going to call them as, say, outward normal. Okay. And those which is inside it, I am going to call them inward. I'm going to call them inward. And again, remember, if I consider the lower hemisphere here, these are still outward normal. You have to remember this. Okay. So in the lower hemisphere, the inward normal, they are going to be in these directions. Is it okay? Fine. So now, what I would like to do, I would like to, surface integral of vector field. So this is what I'm going to do. This is what I'm going to do. Okay. So here I'm going to rope in some concept of your fluid dynamics. Okay. And don't get afraid. Don't get afraid. It is going to be pretty straightforward. And only after that, I will move to that concept. How much time do I have? So maybe what I'm going to do, maybe I'm going to start this in my next class. Okay, so surface integral of vector field. Surface integral of vector field. So maybe before that, let me think about this. See, suppose I consider this sphere. So now, if you write this any point on the sphere in terms of, so x squared plus y squared is equal to, say, a squared. A squared. So if you write it as phi theta. So so that means this is going to be your a sine phi cos theta, then a sine phi sine theta, and then a cos phi. So you will see that if you consider the unit normal from this, this I am leaving as a homework, you can easily do. So this will come out as, I think it is simply going to be this 1 by a, this r. Again, I'm going to get this. Okay, so it is going to give you some scalar multiple of that. So now, what is happening out here? Suppose we are considering the sphere. So then you take any point on the surface of the sphere. So then you join this point. So this is your radius vector. Isn't it? So then you will see that here it is in the direction of the normal, because I exactly cannot show you here. So this radial vector coming from here, it is exactly going to be the normal to the surface. So that is why this happens. The radial vector itself is normal to the surface of that sphere. So as you know that, in some of the slides there were something like an interesting example. So in my next class, what I'm going to do, I'm going to deal with surface integral of vector fields, and that is going to lead me, hopefully, in my next class to Stokes theorem. Okay, so then I will see you in my next